Hello all, welcome to the hands-on series on Fundamentals of Generative AI and Large Language Models, Theory and Practice. In today's session, we will be seeing the implementation of Cycle GAN, which is the Cycle Generative Adversarial Network, which is a variant of the traditional GAN. In our previous sessions, we have seen the working of traditional GANs, which makes use of one generator and a discriminator. From the image dataset what is given to a generator, it tries to generate fake images. Both the real image and the fake image, when given to the discriminator tries to classify both of them and does some prediction. So, the discriminator tries to classify whether the given image is a real image or a fake image. So, in this process there is one generator and a discriminator. And when we talk about the laws pertaining to traditional GANs, it is the generative laws as well as the discriminative laws. In case of Cycle GAN, which is a variant or advanced version of GANs, we make use of multiple generators and multiple discriminator, because the entire process of Cycle GAN is image to image translations. That is, we try to have some images from domain A, we have images from domain B. Only domain A will be given during training to one of the generator. Domain B images will be given to generator 2 while training, but the generator A should generate the images pertaining to domain B, and generator B should image or should try to have the images or try to create fake images pertaining to domain A. So, in this process what happens is the fake images created by generator A as well as B will be given to discriminator A and B. So, totally the laws pertaining to the Cycle GAN includes generator A laws, generator B laws, discriminator A, discriminator B laws, and whatever process involved from A to B or B to A, that is called as cycle consistency laws, and how much identical images that are generated, which is called as the identity laws. So, all three losses, that is the adversarial laws, the cycle consistency laws and the identity laws. So, put together will give us the laws pertaining to GANs. So, this is one of the variant called as Cycle GAN. Now, let us see the implementation of Cycle GAN. So, the usual procedure is importing the necessary libraries. So, let us make use of PyTorch, which is one more open source deep learning framework. So far we have seen in our previous implementation we made use of Python programming language, but we have not used the PyTorch. Instead we have used the TensorFlow or the Keras package. So, let us have a different PyTorch, that is a deep learning framework, in our implementation, and let us see how is it different from the normal TensorFlow or Keras, maybe in terms of the computational complexity or maybe in terms of the implementation or the execution time when it makes use of the CPU or the GPU. So, let us start with the implementation. So, importing the necessary libraries, we import the PyTorch, which is a open source deep learning framework generated or developed by Meta or Facebook. Then we import from the PyTorch or the torch, we want the neural networks. So, in short torch.nn is called as NN. Then we import optimizers from the PyTorch framework, that is why we have this optim as a short form for optimizers. Then from the torch computer vision package, we import the data sets as well as the transformations. So, what data set we are trying to use here is the STL10 data set. STL10 data set is a benchmark data set which can be used for image to image translation, because it has 10 different classes of images of animals. So, since we have to use only 2 domains here to have the Cycle GAN, we are making use of horse images under domain A and deer images under domain B. So, and STL10 has more than 10,000 images. To reduce the computational complexity, we make use of only 400 images both in domain A as well as domain B. So, then we import the data set, which is that STL10 data set, in order to have certain transformations on the image, because we know that images are the raw images and it requires some kind of transformations, maybe scaling of the images or rotation or some angle transformation or cropping of certain areas. That's why put together we have a package, or we have a function called as transforms coming from PyTorch computer vision. Then from PyTorch computer vision utilities, we make use of grid. So grid is required in order to have multiple images in one particular figure. That's why we make use of grid, so that we may have 10 cross 10 images in one particular grid or one particular figure. And then PyTorch utilities data, we make use of the data loader, data set and the subset. So data loader is required if we are going for the deployment case. Suppose we are using some GPUs like RTX or Blackwell, then we can use data loader. But here let us see how we can make use of this even though we have the T4 GPU. And we make use of data set as well as subset. So why this data set is required? Because it's a readily available data set, or from the UCR repository we are making use of this data set. That's why we need this data set. Now coming to the subset, as I already mentioned, we wanted only two classes of data or two domains of data. That's why we are extracting only a subset of the data. That's why we make use of the subset function. And for data visualization purpose, we make use of matplotlib.pyplot. In short, we call it as PLT. And to generate some random number or random noise, we need this random function, as well as to ensure that this PyTorch works under our required operating system, we make use of OS as well. So let me make it clear here. Whenever we use PyTorch, it is slightly different from our TensorFlow or Keras package, and we should make sure whether it is compatible with our CPU or if not the GPU. That's why we make use of this operating system package as well as the data loader and makegrid packages. Also, we are making sure if we have CPU connection or GPU, that's why we have this additional two lines here, device equal to, from PyTorch we make use of device, whether CPU is available or GPU is available. So if GPU is not available, then immediately it will switch or convert into CPU, so that it doesn't stop implementation. So these are the initial importing of the libraries. Now coming to step number 1, that is initialization of certain values. So let the number of epochs be 20 in order to reduce the computational cost, and let the learning rate of the model be 0.0002. We have kept it very less because cycle GAN involves learning images which are unpaired, unlike our traditional GANs. In case of traditional GANs, we give the real image and we ask the generator to generate the fake images from the given domain. Unlike the case of cycle GAN, we give domain A images, but the generator has to generate the fake images corresponding even to domain B. That's why we keep the learning rate as very slow. Otherwise, it will converge very fast, and in the process of converging to a very less loss value, it may generate really fake images. That's why we keep it very low. And batch size is equal to 4. So we consider only 4 images at a time. Now coming to step number 2, loading the data set. As mentioned earlier, we are making use of STL10 data set, which is an animal data set comprising of 10 classes. That's why the name 10 here. Out of which we are choosing class number 6, which happens to be the horse data, and also we are choosing class number 4 data, which happens to be the deer data. So we configure or we treat horse images under domain A and deer images under domain B. Once we have loaded the data set, we have to do certain pre-processing on the data set, because the data set is a raw data set. So we try to compose all the transforms or transformations like resizing the image, cropping the image, converting the image into tensors, or normalizing the image into one transform called as compose. So let us have one composition which comprises 4 different operations. So one after the other, all these operations has to take place. So given image 256 cross 256 pixels, we are resizing into 96 cross 96. So we are trying to compress the image first of all, then cropping so that we have only 96 pixels in width and 96 pixels in height. So that is required soon after resizing. And the main transformation what we are doing is converting into tensors, because PyTorch does not make use of numbers or does not make use of arrays. Instead it makes use of tensors. So when we talk about tensors, the image representation, which is the normal representation for a color images, width into height into channels, or sometimes height into width into channels. But in case of tensors, it is always the channel coming first, followed by the height and then the width. And then we try to normalize those values in the range -1 to 1, because somewhere we can make use of the tanh function where the values lie between -1 to 1. That is why deliberately we try to normalize the values between -1 to 1. So in the process of normalizing, we do it for a color image. That is why we have the value as 3. The first value represents the mean, that is 0.5, and the second value 0.5 represents the standard deviation. So normalized value will be x minus the mean value, which is 0.5, divided by standard deviation, which is 0.5. It is applicable to all 3 channels. So let us take one example and see how exactly this composition of transforms take place. Given any image, let me take a 3 cross 3 image, values lying between 0 to 255. So I may have value as 0, 0 and then 10, maybe this is 250, 255, 20, 15 and 10. So this image, which is ideally 256 cross 256, I have taken only 3 cross 3. This has to be resized into 96 cross 96. So once this is resized, usually our normal representation is this happens to be width, this happens to be height. Since it is RGB image, we have 3 channels pertaining to red, green and blue. This representation will turn into 3. So this represents the number of channels as well. So in case of PyTorch, the transformation will be channels followed by height and then the width. So what happens is, this is 3 cross, height will be 96 and the width will be 96. So this representation is the tensor representation. And now from this tensor representation, if I take the tensor representation, once again I have different values. Say this is 10, 20, 30 or 255, 0, 255, 0, 0 and 1. If I take this way, then the normalization process will be this way. I will take the first value. So normalized value for this 10 will be the actual value minus mean divided by the standard deviation. So what happens for the value 10? It is value 10 minus mean, which is 0.5 divided by 0.5 in our case. But this has to be repeated for the red channel, the green channel and the blue channel. That is why this has to be done into 3. In the formula what we have seen in the code, we have multiplied both the mean as well as the standard deviation with the value as 3. So this is the initial pre-processing that we have to do on the STL10 dataset. So now printing of downloading the STL dataset after all these transformations. So we can print that message, download has to be true, if not throw the error message. Now coming to filtering of the horse and the deer image. So as mentioned earlier, it has more than 400 image, but we are comprising only up to 400. So 0 to 400, so it includes 0 to 399, which is totaling up to 400 images. So horse. What is the horse dataset or domain A dataset? It is a subset of all the data that we have downloaded. For I and values having x as well as y in enumerate data if y equal to 6 is to 400. So we are taking subset of the data and every index varies from 0 to 399 in the class label 6. In the process of taking all the data, we have to enumerate. That means we have to concatenate one value after the other. So, this is the process of enumerating. Similarly, what is our domain B data? It is a dir data, which is subset of the data. Once again, our index value varies from 0 to 399. We have to consider both the x and the y values. That means we have to consider the figure as well as the label, and we have to concatenate all the values or all the images. So, likewise, we have 400 image under domain A and 400 images in domain B. So, we have to print how many are the domain A images and what is the length of the domain B images. So, it will be 400 and 400 each. Now, data set that randomly pairs one horse with one deer. So, this is what I was mentioning earlier. We have unpaired data because horse corresponds to y equal to 6. So, class label is 6, for deer the class label is 4. Now, we have to create random pairs so that the generator generates the fake images. So, how do we pair the data set? So, we make use of domain A as well as B, all the information or self information pertaining to domain A and B, and we have to return the maximum value of the length of the data present in domain A as well as B, and in every iteration we have all the images in A as well as B. So, while pairing, what we do is we do not consider the y part, we ignore the labels, because the discriminator has to guess whether it is a deer image or a horse image. If it is a deer image, whether it is a fake image or the real image. If it is a deer image, whether the given image is real or fake. So, that has to be guessed by the discriminator. So, that is why the labels are ignored. So, whenever we need to ignore anything in Python, we make use of this underscore. So, now self information or the information contained in domain A. So, it is based on the entire length of A, and now randomly generate some integers starting from 0 up to the length of all the images present in B minus 1. So, minus 1 is required because the length will be 400. We want from 0 to 400, that is it becomes 401 images, and then make it minus 1. So, that we have values from 0 to, index varies from 0 to 399. So, finally, return all the images of A and B, both the domains. Now, pairing the data set. So, we pair both the horse and the deer data set, and we consider it in the loader called as a data loader or simply a loader. And when we pair the data set, we make use of batch size so that we need not go through all the 400 images in one stretch. Instead, we can have batch size, so that if we have a batch size as 64, first 64 images will be considered, the epochs or the training of the data takes place on those 64 images, then weights will be updated for those 64 images. So, instead of having a very complex model, we can restrict to batch size as 54 or 64, but in our case we have taken only 4 images at a time. And shuffle equal to true, it is very much required because otherwise there will be memory mapping, that is image A or discriminator A knows that the image has come from domain A, discriminator B knows that the image has come from generator A. So, in order to avoid that memory mapping or memory copying, we can say, we have to make the images shuffle, so that there is no one neuron understanding the memory units of the other neuron. So, in that process we want the number of workers as 2 because batch size is 4. Since batch size is 4, we want in multiples of 2 only. Now, printing of batches per epoch, how many batches we are consider for every epoch. Now, coming to having the generator and the discriminator. So, as mentioned earlier, in the cycle GAN, we make use of 2 generators and 2 discriminator. So, we can call this as, suppose domain A has horse image, we have generator A which has to create fake deer images. Then we have discriminator which tells if it is a fake image or a real image. Now, real image is domain A image, fake image is B. So, how do we generalize this term is, this is discriminator BA, but this is generator AB, because real images are A, it has created fake deer images. So, this can be called as generator AB and discriminator BA. So, when we do it vice versa, what we do is we take domain B images, which are the deer images. We consider generator B because it is getting the information from domain B, but it has to create fake images from domain A. So, this is generator BA. So, somewhere it generates fake horse image, which the discriminator has to learn. So, discriminator AB. So, totally we have 4 losses: generator AB loss, discriminator BA loss, generator BA loss and discriminator AB loss. So, these are the 4 loss, and put together this can be called as cycle consistency loss, because it is a cycle of domain A going up to domain B, or we start with domain B and come to domain A. So, this is a cycle of processes which involves the generator and the discriminator. So, put together this kind of loss can be called as cycle consistency loss. So, now let us set up generator AB, discriminator AB. So, what is this generator? So, we create a module called as generator from the neural networks. That is why we have a class generator and the module name is got from the neural networks. So, it comprises, we always know a generator comprises of an encoder and a decoder. So, initially we compress the image and then we decompress the image, nothing but a reconstruction takes place. So, what does our encoder comprise of? Encoder will compress the image. So, we initially start with the convolution process, we normalize those images and then one more convolution. So, we start with the number of channels as 3, number of neurons as 64, number of filters as 7 and padding equal to 3. Then we have the batch normalization, and batch normalization value is equal to 64, and ReLU activation function, because we have to avoid whichever negative values we have, because always images should have the value from 0 to 255 only, which are positive values. ReLU is one activation function which makes use of maximum value of 0 and the actual pixel value. So, if the actual pixel value is a negative value, maximum of 0 and that negative value will be 0. If the pixel value is a positive value, then 0 comma that positive pixel value will be a positive value. That is why we make use of ReLU activation function. Then the next convolution layer comprising of 64 neurons, 128 filters, such filters we use, and then the filter size is 3 and we make use of stride equal to 2. So, we try to increase the stride so that we avoid one window in between the 2 strides, and padding is necessary so that we do not lose the edge information. Now, coming to one more normalization, we increase the normalization size, that is 128 neurons, once again the ReLU activation function, convolution 128 filters and then 128 neurons, 256 filters, 3 cross 3 is the window size, stride being 2, padding equal to 1. So, we should always remember that the stride value or the padding value is left from one user to the other user, because sometimes we try to overlap and fix onto stride equal to 0. Sometimes we need to avoid the in between content between 2 different pixels or 3 different pixels. That is why we increase the stride value. So, it is always the trial and error basis. So, there is no logic behind why to use stride equal to 2 or stride equal to 1. So, whenever we are confident enough on the generator, or we are confident enough on the data set, what kind of data set we have, we can always have a bigger or a larger stride. So, finally, we have this normalization making use of 256 neurons and the ReLU activation function. Now, finally, we have this transformer module. So, convolution 256 neurons, 256 window size, and 3 channels we make use of, and padding equal to 1, followed by the normalization and ReLU. So this is the transformer unit, or the we can call it as a whatever transformation we have done on the original image. So likewise we do it 4 times because we have made use of 3 convolution. So we make use of 4 convolution here, 3 plus 1 always. Whatever encoder we have created, that is 3 convolution what we have created, for those 3 convolution we should now have the decoding part. Now what is the decoding part? It is always the decompression. So in case of compression, we start with a small number of neurons and reach up to large neurons. So if we see here 3 neurons, 64 neurons, and then 128 neurons, or 3 filters, 64 filters, or we can call it as 128 filters. Now it should be the reverse way in case of decoder. We start with 256, then we come down to 128 and 64. So the entire process of encoding and decoding is such a way that the filtering is low level filtering when we start with the image. Then low level filtering is done, we go with the mid level filtering and then the high level filtering. So it is a deep feature extraction what happens in case of encoder. Now in case of decoder, it has to be a reverse process. That means whatever feature extracted, from that we have to gauge the patterns, we have to find the patterns out of it. So it becomes like a decompression or a de-encoding. That's why we call it as a de-encoder or decoder, in short called as decoder. So finally we want all the values to lie between -1 and 1. That's why we make use of the tanh activation function. So ReLU will have all the values. ReLU activation function is required in order to avoid the negative value. So it functions in this way, it is maximum of 0, x. Suppose we have a negative value, say -2, then what happens is maximum of 0, -2, it happens to be 0. Say if we have a value as 10, a positive value, maximum of 0, 10, it happens to be 10. So in both the cases the positive value is retained. So negative value converted into 0, positive value retained as it is. So this is the ReLU activation function, whereas tanh activation function always tries to have the value between -1 and 1. So 0 can be called as the mid or the median value. That's why we expect mean to be in and around 0 and standard deviation somewhere around 1, so that it follows a Gaussian distribution, something like this. So mean should be somewhere centered around 0, and this could be plus or minus 1 standard deviation, 2 standard deviation, or 3 standard deviation, based on how much we are able to accept the outliers. So outliers means when we say outliers in terms of numbers, it is corresponding to the fake or very fake images. So this is all about the encoder part. So this is all about the generator part. Now coming to the discriminator. Discriminator has to guess whether the given image is a real image or a fake image, and it also has to guess whether it is from domain A or B. So how do we define the discriminator? Once again, from the neural network module called discriminator, we create a class called as discriminator. It is a layer by layer, stacking of layers by layer. That's why we have the function called as sequential from the neural networks. So what is happening? We make use of 4 convolution layers. Once again, this is low level filtering to high level filtering. So in case of low level filtering, some of the features that could be extracted or guessed could be lines, points, or edges. Mid level filtering tries to have some patterns, or maybe it can also focus on shape of the image or texture of an image. But while coming to high level filtering like 128 and 256, it is able to get some contours on the image or the unique patterns. So suppose we talk about a zebra, then there are unique contours called as contours of blue as well as black. So it is able to identify those contours or circles. Suppose we are talking about about maybe cat, it has fur. So based on the texture, it is able to discriminate. So we start with a small point on an image and try to come up to the texture or the various contours present in the images. So that's why we have different levels of filtering, low level to high level filtering. Once again, the stride and padding is left to the user. We can use different values of striding, how much we have to take the window size. And we make use of the leaky ReLU function. So the difference between leaky ReLU and ReLU is ReLU will try to convert even the negative values into positive values. But in the process of converting, some of the activation functions or some of the neurons may be lost, or what we say is most of the values will become 0, so there is no learning which is happening. In case of leaky ReLU, some leaky values or even a small alpha values will be tried to retain. Maybe the value could be 0.001, due to which the neuron will be active. So the activation function will be active, nothing but the neuron will be active, and there will be some processing happening on every neuron or every hidden unit which is present. That is why we make use of the leaky ReLU function. So now coming to creating the 4 models: generator AB, generator BA, discriminator A, discriminator B. So this is already mentioned earlier. What is generator AB, what is BA, similarly what is discriminator A and discriminator B. So it is also given in terms of comments here. Generator AB means we have domain A, horse images, from which deer images will be generated, that is the fake deer images. Generator BA means it takes the input from domain B, which is deer, and tries to create fake horse images. Discriminator A will ask, or it will fetch for whether it is a real horse, whether the data is coming from domain A. What will discriminator B do is, it is looking for real D, that is images from domain B. So we have to send all the discriminator or the generator what we have considered to the CUDA device. That is why we have this function to device. So once this is done, we have to print the number of parameters corresponding to generator as well as parameters corresponding to the discriminator. So we know that always there will be some operations in different hidden layers except the input layer. Input layer takes only the input, but after the input layer we have the hidden set of hidden layers, multiple hidden layers, and then we have the output or the fully connected or the dense layers. So at those layers different operations will take place. So the weight updation is based on what inputs we have, how many hidden neurons we have, plus whatever bias associated with those neurons. So based on that we have this parameter calculation. So let me show one simple example, or how do we mathematically represent those parameter calculation. So always we should remember the number of parameters will be equal to input, whatever input that is going to that layer, maybe input layer or hidden layer, into the hidden neurons plus the bias associated with those neurons. So this is the parameter calculation. So such parameter calculation holds good both for the generator as well as the discriminator. So now coming to the loss functions, there could be mean square error, there could be L1 loss also. So a mean square error is the GAN loss, which is already mentioned, which can be called as a adversarial loss also. The L1 loss, which is the cycle plus the identity loss. So as mentioned earlier in the session, there is cycle consistency loss as well as identity loss. So both can be called as L1 loss. Now what are the different optimizers related to the generator and the discriminator? So we have one of the optimizer related to the generator, which is the Adam optimizer. So we have to list all the parameters that is calculated in the previous line here, as well as all the parameters related to the second generator, that is BA, and whatever learning rate that we have set, that is 0.0001, and whatever beta, that is the bias values that is set. Similarly, the beta 1 and the beta 2 values. We know that the Adam optimizer is based on the mean calculation as well as the variance calculation. So, in the process of mean calculation and variance calculation, there are two scalar values or constant values associated with this, that is 1 and the second one, beta 1 and beta 2. Now, coming to optimizer related to discriminator A. So, all the parameters that are involved in the discriminator A plus its learning rate and beta 1 as well as beta 2 values. Similarly, even for discriminator B, we have beta 1 and beta 2 values. So, in the session of autoencoders, we have already seen why we should have beta 1 value as 0.5 and why beta 2 value should be nearly equal to 1, somewhere like 0.99 or 0.998. So, we have already seen in case of autoencoders. Now, we consider all the samples which are existing in our OS, that is we have created a directory from the existing OS and we consider all the samples in order to optimize with the help of Adam optimizer. Now, coming to the training part, training on the samples, that is the input samples. So, print the starting of the training, we can print the statement for every epoch in the range 1 and at every iteration it will be epoch plus 1. So, we have to load all the horse images, the deer images from the loader, and the real and the fake, we have to have two different folders in order to comprise the real image and the fake image. So, based on the real and the fake image, then we have the loss calculation. So, real image we have to append ones, fake image we have to append zeros. That means, in case of real images and fake images, we have to start concatenating 1. So, if until we have the real images, the dense vector will have values as 1 only. Suppose one fake image comes in between, then the dense vector value will be 0. Same thing for the fake also, we should create one dense vector. So, if it is real, then definitely this value will be 0. So, these many values will be 0. Since this is 1, the opposite will be 1. So, this is a vector corresponding to the real image and this one to the fake image. So, now coming to training the generator. So, as mentioned earlier, there are two different generators, one for the horse, other one for the deer. Based on whether image is coming from domain A or B, we have 4 combination. So, horse to fake deer generation, deer to fake horse generation. Similarly, fake deer back to horse generation, fake horse that is created back to deer generation. So, we have 4 different combinations. So, this will whatever loss associated with respect to reconstruction, it is the reconstruction loss for the horse and reconstruction loss for the deer. So, put together the losses are the mean square error loss corresponding both to discriminator B and discriminator A, and the cycle consistency loss, that can be called as the L1 loss corresponding to the reconstruction loss as well as the real image. Likewise, we have 10 different classes. Similarly, L1 of that is reconstruction loss for the deer as well as the real deer images comprising of 10 different classes. And the identity loss will be whatever generator we consider, that is the AB generator and the deer image that is generated plus the actual deer images, because how much identical it is. Similarly, L1 corresponding to horse image that is generated and how many real horse images were there. So, this shows the identity or similarity, that is why the name is identity loss. So, total GAN loss for a cycle GAN loss will be total GAN loss, that is a mean square error loss plus the consistency loss plus the identity loss. So, in the backward propagation we have to take this loss of the GAN and then the optimizer, whatever optimizer, in our case the Adam optimizer that is being used, it will update the weights. So, the relationship between the optimizer and the gradient values or the learning rate is this way. We have the new weights that is calculated in the back propagation, that will be corresponding to the old weight minus eta into del L by del W. So, this del L by del W corresponds to the gradients. So, how much loss incurring due to the change in the weights, that has to be calculated. So, that is back propagated. So, how much change in the weights has to be done, what is a new weight. So, that depends on the old weight minus the eta value. And del L by del W depends on optimizer, and our optimizer is Adam optimizer, which is based on beta 1 and beta 2 values. So, totally what is training of discriminator A, what is the training involved in discriminator B. So, training of discriminator A means it is the mean square error associated with discriminator A, which takes the real image into account, mean square error for discriminator A, which takes the fake horse image into account. So, multiplied by 0.5, because we also have the discriminator B. So, two different discriminator. Similarly, discriminator B means one which is associated with the domain B. We have the mean square error for the deer images that is coming from domain B plus the real images which are already generated by the generator. Similarly, mean square error for the fake deer images that is created and the fake images. Since we are considering both the discriminator, the weightage is given equally 0.5 and 0.5. So, finally, printing of the epochs, printing of the generator loss, discriminator loss. So, put together we have one generator loss now, which considers the adversarial loss, cycle consistency loss and the identity loss. So, showing the results after every epochs. So, this is required while printing of the image and the epoch values. So, we consider the different iterations, which is based on how many images we are loading, and every iteration it has to pass on to the next image. So, that is why we have this function called as next. So, we have 4 images to be displayed in every row, that is why we have index is to 4. So, 0 to 3, so 0, 1, 2, 3, which corresponds to the real image coming from one of the domain. Fake images created by the generator, that takes the second position. Whatever image the discriminator gets, that is takes the third placeholder, and the fourth image will be whether the discriminator is able to classify them. So, that is the fourth placeholder. That is why we have 4 placeholders here. So, finally, we have forward and backward propagations. In the forward, we have the deer image, the horse image, and in the reconstruction, the horse image and the deer image. So, we can see it in the comments: horse to deer, deer to horse, cycle back to horse and cycle back to deer. So, this process is already explained in the text editor. Now, coming to displaying, what are the different images that we need to see in the while we plot the images. So, we have the real horse, fake deer and reconstructed horse. Similarly, original image is always there. Then we have the real deer, the fake horse that is generated and the reconstructed deer. So, we have to make a grid of these many things. So, we have different categories from PyTorch. CAT stands for categories. So, different categories are horse, fake deer, reconstructed horse, deer, fake horse and reconstructed deer. So, 4 images. Normalized value true, because we have already normalized it in the value as -1 to 1. Now, to get back, we have to have the tensor values. From the tensor values, we have to get the pixel values. That is why we have to consider the normalized value. So, let us have a figure of argument figure size with the width as 12 inches and height as 6 inches. So, let us show in the form of a grid and permute. Permute means we want 1 row and 2 columns and different placeholders. So, let the axis be off. Let us not give any naming for the x axis or the y axis. We have to just display the original fake image and the real image. That is why we keep the axis as off, and the different titles. Row number 1, the original image, real, fake and reconstructed. Similarly, row number 2. Likewise, we want the title to be given. Let the font size for the title be 10. So, all these are some of the arrangements or settings that we do for plotting. Plot tight layout means it shouldn't go, whatever images that we display shouldn't go out of the layout, out of the layout of that is already described here. We have already described as 12,6. So, we want to save the figure, we can save it in our system, that is why this kind of setting we are doing as a PNG with the resolution as 100. Then we have to show the image. So, training both the generator AB and BA. So, all the printing to be done as and when we save the models, that is generator and the discriminator. After every epoch we should have a message as saving the models. So, we are saving the dictionary values of generator AB, the dictionary values of BA. So, what is the dictionary consist of? It has a key and the value. Key means it shows which domain it has come from, value means whether it is real or fake. So, we create a dictionary of two items, one is the key and the other one is the value. And whatever images generated by generator AB, that is saved in this path, that is G underscore horse to deer translation. Whatever fake images that is generated by generator BA is saved in a path, and the path name is deer to horse. So, this is one more image translation. So, basically we started with domain A images, domain B images separately. Now, with the help of CycleGAN we have done a image translation, A to B and B to A translation. So, finally we have to print a message called as saved, we have saved both the paths. So, whatever printing we have done, we have the output for all of them. Downloading the STL data set, STL10 data set, we have horse images which are 400 and deer images which are 400 in number. Number of batches we have taken per epoch is 100. Why? Because we have taken batch size as 4 and we have 400 images. So, 400 divided by 4 we get it as 100. Number of generator parameters are 3.1 million parameters that we need to calculate. And for the discriminator the number of parameters are 0.7 million. So, once again let us recall, parameter calculation is based on number of inputs that we are considering into the number of neurons associated with the hidden layers plus the bias associated with the hidden layers. And we start the training. So, we have to run 20 epochs, and these are the losses pertaining to generator, discriminator A, discriminator B. So, what is happening at epoch 1? We have the original image, the real horse, the fake deer image and the reconstructed horse. Similarly, the real deer, the original image, the real deer, the fake horse and the reconstructed deer. So, likewise this display we have to continue up to the last epoch. So, the different epochs here. We can see the different epochs and the associated generator loss, discriminator A loss and discriminator B loss. So, we have run 20 different epochs. We have made the model, the CycleGAN model to run or go through the 400 images 20 different times. So, finally, the generator loss is 5.12, the discriminator A loss is 0.2 and discriminator B loss is 0.16. So, we say that the discriminator B is better when compared to A. So, it is able to correctly classify the deer and the horse image. So, we have saved the model for both the path as that is horse to deer as well as deer to horse. So, this is required. The GAN images or the images created by both the generators are required when we process onto new set of images. So, we can use this as a base image and we will be able to make use of other GANs and create some more fake images. That is why we should always save the fake images created by the generator. So, this is all about the implementation of CycleGAN, which is Cycle Generative Adversarial Network. So, as mentioned earlier, Cycle Generative Adversarial Network is a variant of traditional GANs which makes use of multiple generators and multiple discriminator. So, this is the way it is different from traditional GAN. So traditional GANs, the reconstruction loss will be very high because we make use of only one generator and a discriminator. Unlike in case of a cycle GAN, we try to train the real or the fake images by having multiple combinations of generator and discriminator. So when we try to compare this with the traditional GANs or the DC GANs, what we have seen in our previous sessions, this GAN is helpful in image to image translation. So when we say image to image translation, it is required to have images only from one of the domain, and with the knowledge that is acquired by the GAN from one of the domain, it is able to have a fake image from the other domain. So in our case of STL10 dataset, we have made use of only two domains, horse domain and the deer domain. By taking only the horse image, it is able to construct a deer image. By taking the images only of the deer domain, it is able to reconstruct or construct images pertaining to a horse. So this is called as unpaired data, or cycle GAN makes use of unpaired data. So this is all about cycle GAN. Thank you.